Welcome to our presentation on reproducing the paper Developing Personalized Models of Blood Pressure Estimation from Wearable Sensors Data Using Minimally Trained Domain Adversarial Neural Networks by Zhang and colleagues. Our goal was to test if we could recreate their approach for personalizing blood pressure monitoring with minimal training data. The original paper, published in 2020, introduced a novel approach to personalized blood pressure estimation. The authors used domain adversarial neural networks to create models that can adapt to new users with just a few minutes of calibration data. This was a significant improvement over previous approaches that required extensive calibration time, making it more practical for everyday healthcare applications. The problem addressed is significant in healthcare. Blood pressure monitoring outside of clinical settings provides better prognostic information, but current devices are obtrusive and difficult to use continuously. A key challenge is the lengthy calibration time needed for personalization. The authors proposed using DAN to learn domain-invariant features across users, enabling rapid adaptation to new users with just 4 minutes of calibration data, instead of the typical 10+ minutes required by previous approaches. The DAN architecture consists of 3 main components. First, a feature extractor using an LSTM with 30 units processes bioimpedance signals to create useful representations. Second, 2 task-specific networks estimate diastolic and systolic blood pressure. Third, a domain classifier tries to identify which subject the data belongs to. The key innovation is the gradient reversal layer, which reverses gradients during backpropagation, forcing the feature extractor to learn subject-invariant features. This adversarial approach allows the model to focus on blood pressure patterns rather than subject-specific characteristics. For our reproduction study, we faced an immediate challenge. The original dataset wasn't publicly available. We created a synthetic dataset that matched the statistical properties described in the paper, simulating bioimpedance signals for 11 subjects. We implemented the full DAN model architecture and followed the same training and evaluation protocols. Our synthetic data included realistic individual variations and transitions between different activity levels to mimic the physiological patterns described in the original study. We implemented our study using Python 3.9.5 and TensorFlow 2.40. The model follows the LSTM-based architecture described in the paper with a high dropout rate of 0.7 to prevent overfitting, particularly important given the limited training data. We used a learning rate of 0.003, batch size of 100, and 30 LSTM hidden units. The training process used a multi-objective loss function that balanced blood pressure estimation accuracy with domain invariance, with a domain classification weight of 0.1. When comparing our results to the original paper, we observed similar trends but with higher error rates. For 3 minutes of training data, the original paper reported RMSE values of 4.80 mmHg for diastolic and 7.34 mmHg for systolic blood pressure. Our implementation showed higher errors, 9.33 mmHg for diastolic and 16.98 mmHg for systolic. This gap narrows with more training data but remains significant, especially for systolic pressure. Despite these differences, both studies show consistent improvement as training data increases from 3 to 5 minutes. The ISO standards for blood pressure devices require at least 85% of measurements to be within 10 mmHg of reference values. The original paper met this threshold for both diastolic and systolic pressure with just 4 minutes of training data. In our implementation, only diastolic blood pressure reached the standard, and only with 5 minutes of training. Our systolic estimations remain below the threshold even with 5 minutes of training. This highlights the sensitivity of the model to implementation details and data characteristics. As an extension to the original study, we tested the model's ability to interpolate across missing blood pressure ranges. We intentionally withheld specific ranges during training and evaluated performance on those ranges. We found that the model can generalize across small gaps of 3 to 5 mmHg reasonably well, but performance degrades with larger gaps of 7 mmHg or more. Interestingly, the model handles middle blood pressure ranges better than extreme values, suggesting that providing low and high blood pressure examples during calibration may be more important than mid-range values. In conclusion, our reproducibility study was partially successful. We were able to implement the core architecture and confirm several key findings from the original paper. DAN does improve performance over simpler baseline methods, and training data can be reduced while maintaining reasonable accuracy. However, we couldn't match the exact performance reported in the original paper, especially for systolic blood pressure. Our results suggest that 4 to 5 minutes is indeed the minimum viable calibration time, aligning with the original paper's conclusion. For future work, developing better subject similarity metrics could improve domain selection and further reduce calibration requirements. Thank you for your attention. Our implementation is available on GitHub at the link shown. We're happy to answer any questions about our reproduction study or the DAN approach to personalized blood pressure estimation.